Hello everyone, my name is Chavoosh and I'm from University of Arizona. In this talk, I present a real-world comparison between the NDN testbed and two leading CDNs on the market, Aryaka and Fastly. This paper provides an assessment of where the standard NDN deployment stands today and points to future directions. The current internet was designed as a transport network. A transport network only connects endpoints to each other, so applications need to tell the network what machine they want to connect to instead of what content they want. Back in the time, this design made sense because a machine in the network needed to access another machine's resources like tape drive, printer, or processors. But today, it's not the goal any longer. Instead, the majority of applications just want to share and retrieve content, so they don't care where in the network the content comes from. This is why content networks emerged. A content network understands what content has been requested and tries to retrieve it from anywhere in the network, whether a cache or the producer. In a content network, some or all of the machines can cache, and requests are forwarded based on the content name rather than the destination's IP address. To implement a content network over the internet, which is an enormous transport network, CDNs have been deployed. So a CDN tries to build a content network on top of the internet with the minimal changes to the internet. ICN and NDN in particular offers a new way to build a content network, and architecturally, NDN offers a simpler and more secure content network by supporting multiple features for content distribution at the forwarding plane. Thus, in this work, we attempt to compare the content networks built by CDNs and NDN to better understand their strengths and limitations. It's also important to mention that today's CDNs are highly mature complex systems with many different features, while NDN is merely a research with a few prototype software with no production level fitness. So we cannot compare them in all aspects as if we are comparing two end products. Instead, we limit our comparison to the most basic feature of content networks, which is the caching and retrieval of static contents. To do so, we deployed an adaptive video streaming service and streamed a large number of videos over Akamai, Fastly, and NDN testbed from 4 different continents for 2 weeks. We captured terabytes of traffic on the end user side and the origin side from each network and compared the performance of the networks in terms of quality of experience, origin workload, failure resiliency, and content security. In the future slides, I will present the results for each of these metrics. To compare the quality of experience, we compare these networks in terms of video resolution and startup delay. This figure shows the video resolution that the users experience in different locations from different networks. The x-axis shows the network type, where A stands for Akamai, F stands for Fastly, and N stands for NDN testbed. As we can see, Akamai and Fastly offers 1080p resolution, which is the full HD resolution, no matter where the end users are. But for NDN, increasing the geographical distance between the end users and the video server, which is located in Arizona, directly affects the video resolution that the end users experience. For example, there is a noticeable video resolution gap between the Canadian end users and Asian end users. And the question is why? To answer this question, let's look at this figure. This figure shows the number of Akamai and Fastly servers that contacted the video servers plus the number of TCP connections that is established for a single video streaming. For example, if you take a look at this point, you can see that during 90% of all video playbacks, Fastly downloaded the audio and video files by establishing more than 38 TCP connection by using over 30 different servers. To put it in a different way, this figure shows a heavy parallelization that Akamai and Fastly used to compensate for the geographical distance between the end users and the video server. Because no matter how many files are needed to play back a few seconds of the video, Akamai and Fastly download all those files at once. In NDN, however, lack of sufficient resources causes serialization, such that the solicited files are downloaded one at a time, back to back. By increasing the geographical distance between the end user and video server, the effect of this serialization magnifies by multiple times. Another quality of experience factor is the startup delay, which shows how long end users wait till the video starts playing back. As you can see, the startup delay through the Akamai and Fastly is mostly below half seconds, but for NDN is mostly over 2 seconds, and for South American end users it's even worse. Understanding why CDNs outperform NDN in terms of startup delay leads us to this figure. The changes in the startup delay mostly come from whether the video is cached in the network, and if so, how far is the cache from the end users. This figure shows the average round-trip time between the end users and the server they're connected to. So as you can see through Akamai and Fastly, the delay between the end users and the server they're connected to was 100% of times below 9 milliseconds. But in NDN, end users could find such a good connection only for 14% of the times. So even if the whole video was cached at the server that the end user connected to, the median startup delay in Akamai and Fastly would be 6 times better than NDN on average, as is shown in this figure. And a clear example of this observation is a high startup delay in South America, because the closest NDN server in that area to end users was 148 milliseconds away. Alongside CDN's large deployment coverage, another reason for CDN's high quality of experience is the optimized software implementation. Compared to CDNs, NDN has been mostly an academic project developed and maintained by the research community. NDN software, at least as of today, is merely a prototype of the technology which delivers the basics of NDN design without any production level fitness or optimization. To roughly quantify the performance of the software implementation on Akamai, Fastly, and NDN testbed, we ran a separate set of experiments to exclude the role of parallelization and large deployment of Akamai and Fastly. But here, for the sake of time, I'm just going to report the results without describing the setup for this new set of experiments. We confirmed that NDN testbed provides end users with the throughput, on average, with a throughput of only 7 megabits per second and 23 megabits per second at the best. But in comparison, we can see that Akamai, in our experiments, we could see that Akamai provides end users on average with a throughput of 96 megabits per second and Fastly 83 megabits per second. And as we can see, there is a big gap between what NDN offers and Akamai and Fastly offer. This observation endorses the lack of software maturity on NDN testbed is significantly limiting its performance in the real world. So just to conclude what we discussed up till here, both Akamai and Fastly strive for two things. The first one is both Akamai and Fastly try to cache the contents less than a few milliseconds away from the end users, and they try to download contents from the origin using their highly optimized software through massive parallelism. Compared to CDNs, current NDN deployment can barely support these two goals due to its software immaturity and lack of large deployment. Now let's compare these networks in terms of the workload they incur to the video server. When we compare the traffic received by the video server from each network during the 2-week experiment, we will end up with this figure. This pie chart shows the total amount of traffic received by the video server from all networks, and each slice in this pie chart shows the contribution of each network to the total amount of traffic. For example, we can see that Fastly is accountable for 38% of the total traffic received by the video server from all the 3 networks. And the big numbers in this figure shows actually compare the traffic load of Akamai and Fastly to that of NDN. For example, here we can see that Akamai incurs 1.77 times more traffic load to the video server than NDN does. There are 2 main reasons that why NDN incurs less traffic to video servers to the video server than Fastly and Akamai. The first reason is a network architecture. NDN testbed does not partition the network, so each request from the end user all the way to the video server has a really good chance to meet the cache on the way. However, in Akamai and Fastly, the network is partitioned to smaller networks, which is called island. The issue is that if an end user sends a request to an island and that island does not have the content, it does not check whether the content is cached anywhere else in the network, and it directly fetches the content from the video server. The second reason is the request aggregation. NDN natively aggregates the request for the same content because of using pending interest table. We also confirmed that Fastly supports this feature, but in Akamai, if multiple end users ask for the same content, it will send all those requests to the video server without aggregating them. This also partially explains why Akamai incurs the highest traffic load to the video server. We also compare these content networks in terms of failure resiliency. In a content network, failure resiliency is measured based on content retrieval performance. It means the higher the chance of resolving a content, the more resilient the content network is. Based on this definition, we measure Akamai, Fastly, and NDN testbed resiliency. In this scenario, each network caches a specific content in some parts of the network, and then the server stops serving that content. Then end users from different locations try to access that content. As we can see in this table, Akamai and Fastly could serve only less than 14% of the requests, while NDN served 100% of all the requests. That is because all the requests over the testbed have a chance of being served by the testbed machine, which is directly connected to the video server, even if the request couldn't find the content anywhere else on the testbed. That is a really good example of when a content is actually available in a CDN, but because of the CDN's network design, the content cannot be served. To summarize what we discussed up till here, we quantify two main issues that come with CDN's network design that cannot be addressed by resource provisioning. The results also show that these two issues are properly answered by the NDN testbed because of its stateful forwarding plane, network design, and unique in-network caching features. As the last metric, we want to briefly discuss security models employed by CDNs and NDN. CDNs, like other TCP/IP-based systems, secure the communication channel between two endpoints by encrypting the traffic at the transport layer, and TLS is probably the most well-known technique here. This way, no third parties can see what content is being retrieved, so the privacy and confidentiality of the content is preserved. By using TLS, CDNs guarantee data privacy. NDN, on the other hand, uses a data-centric security model in which every data packet is signed by its producer at the time the content is generated. This way, any content receiver in the network can confirm whether the content's payload is modified and whether it actually belongs to an authorized producer. So NDN guarantees the integrity of every piece of content in the network. To better understand the comparison of CDN and NDN security models, I'm going to present two common real-world scenarios. But you can find more examples and more details on this topic in the paper. As a first scenario, let's say company X decided to deliver its website to its end users through Akamai. So its end users will contact Akamai servers to access the website. However, the end users' browsers probably refuse to talk to Akamai servers because those servers cannot authenticate themselves as a company X servers. A common approach here is that Akamai asks for the private key of company X. So in this way, Akamai servers can authenticate themselves as a legitimate servers of company X. So end users' browsers will accept talking to them. This is, however, a big security leak because private key is never meant to be shared. This issue is rooted in the fact that end users place their trust in the machine they are talking to instead of the content they receive. In contrast, NDN doesn't have such an issue because the end user can verify the content integrity and its producer, which is, in this scenario, is company X, no matter from where and through what channel the content is received. For the second scenario, you can consider this example. It's very common that CDN companies modify their customers' web pages to embed some controlling information and metadata. Here, the content of the web pages belong to a customer, let's say company X, but they are generated by the CDN servers upon receiving a user's request. To support such behavior, CDNs again need to access the company X's private key. NDN, on the other hand, does not need this. According to NDN's principle, whoever produces the data must sign it. Therefore, content receivers will trust the data they receive only if the entity or the machine that signed it is known as an authorized entity by the original producer. The good news is, by employing a trust schema, NDN enables any producer in the network to explicitly specify what entity or machines in the network are allowed to sign its contents. So considering this example once again, by using NDN security model, a company X could simply specify a CDN company as an authorized entity to sign its content without sharing its private key with the CDN company. This mechanism provides a versatile, general-purpose way to configure trust in the network and can be readily applied to support dynamically generated contents. So, large-scale content distribution can highly benefit from NDN's data-centric security model because this model lets the contents be safely cached and retrieved by any network machine while enabling content owners to explicitly configure the trust in the network. However, probably the main issue of NDN security model is a lack of privacy, meaning potentially any machine in a network can see what has been requested. This limitation can be partially addressed by a hub-by-hub encryption. However, to the best of our knowledge, this issue is an open problem under active research in ICN and NDN community. Okay, I want to wrap up this talk by sharing some important lessons we learned about current NDN deployment to help future research. As I discussed earlier, lack of sufficient hardware and optimized software is limiting NDN's performance. Currently, there are only a dozen servers on the testbed that can relay the traffic of our streaming service, and several of them are old machines without sufficient computation and bandwidth capacity. Besides, we clearly observe that the lack of optimization in NFT significantly overshadows NDN's novel design in the real world. For example, we identified and resolved several major software bugs on the testbed that were throttling the system performance. Just to highlight how important software maturity is, before fixing the bugs, the quality of experience numbers that you saw in the previous slides for NDN testbed were at least 2 times worse. Although some may argue that hardware and software of the testbed do not need to be at the production level, this paper makes it clear that what gives NDN a real shot of being part of the future networking is a production level demonstration and not solely a good design. The second lesson is about applications. At the moment, IP applications and services cannot directly run over NDN. This by itself might not be an issue. However, developing NDN applications is a quite complex and time-consuming process. For example, in this work, we spent several months in developing the NDN version of the video streaming service. And this issue has actually been confirmed by multiple other works in the literature. We believe that at this stage of architectural development, what is keenly needed is to run applications and services for daily internet users on the testbed. This not only encourages end users to use this young technology, but it also allows researchers to evaluate and measure NDN technologies based on real traffic from real users. As a last lesson in NDN, it's fairly challenging to accurately determine the path that interest takes. This is because servers treat routing information as a hint and mostly make their forwarding decision based on their historical local measurement. In this work, we spent many hours learning how the NDN testbed forwards interest. For example, during one video streaming session from London, we confirmed that the interest took 8 different paths to 3 different caches in the network. Although such diversity has some benefits like failure resiliency, its combination with the lack of a sophisticated monitoring system on the testbed makes it significantly challenging to learn how NDN actually works in the real world. We believe deploying a monitoring and debugging platform on the NDN testbed arguably facilitates not only the network management for administration purposes, but also the network measurement and evaluations for researchers and developers. To conclude, a decade of research and development on NDN technology has produced today's global NDN testbed. And for the first time, we evaluated this network in the wild and compared it with 2 well-known CDNs by running an adaptive video streaming service and streaming hundreds of videos from different continents. We argue that quality of experience in these networks is mainly determined by their hardware and software maturity. That is why the quality of experience in CDNs is better than NDN testbed at present. We also demonstrated that features such as origin workload and failure resilience are mainly the products of the design of these networks. That is where NDN outperforms CDNs. And in the end, we believe that having a resilient and scalable content network is not a matter of a distant future. NDN technology has a great potential to realize such a network if accompanied by mature software, protocols, and sufficient hardware resources. Thank you.